we have Amir Safavi-Naini from Stanford. And then the following week will be our last one of the semester with Jen Choi from Wisconsin. So today we are delighted to have Christine Silberhorn, who's going to tell us about nonlinear integrated quantum systems.
All right.
And Christina did her PhD at Erlangen.
So before I do, I want to remind everyone we have two more.
Julie, can you mute yourself? There we go. Sorry about that. Christina did her PhD at Erlangen and then a postdoc at Oxford before returning to Erlangen and then eventually landing in Paderborn, where she now leads a big group doing quantum optics. So thanks a lot. And please put your questions in the chat. And Christina says that she can take them during, so I'll interrupt if there's anything urgent.
Well, let me start with thanking you, Elizabeth, for the introduction, but moreover, for giving me the opportunity to present my work here in this framework. It's quite fascinating. I have looked a little bit through the website for your institute, and I think there's great science going on. Now, I entitled my talk Nonlinear Integrated Quantum Optics, with pulsed light. Now, this is a title which, well, is very descriptive, but doesn't give you the idea of our research theme. And I'd like to start with that. And if you ask me, how would you describe your research? I would say we're exploring quantum networks. Why is that? What do I mean by that? Well, let me first start by explaining to you what a network is, in my opinion. So we have a system, we have different nodes, and then they are interconnected by vertices. And this network, so if you talk about networks, what comes immediately into your mind, I guess, is the internet. But this is not only the only thing, there's also like neural networks, or also if you want to model transport, a network might also be a nice system to study that. What I want to say there is that a network for me is a model system for complex large-scale structure. Now, within this model system, we want to understand what makes this system quantum. And I hope that by the end of the talk, you will see that this is a question which is not actually so easy to answer, and it's quite interesting from a fundamental physics point of view. Now, I'm also coming from the photonics community, and there, the network idea I would describe a little bit differently. I would say we are looking at multi-dimensional photonic quantum system. And this has direct application. One of them is quantum computation and simulation. I will talk a little bit in a minute about that. And the other one is, if you're talking about multi-mode system, is quantum metrology, where we also look at multiparameters. And last but not least, we're talking about photons and photonic systems. And their multidimensional can also be very beneficial because there you can have high dimensional information encoding. So I hope this sets a little bit the scene. Now, let me start by talking about photonic quantum computation. I won't go into detail later on, but this is really actually a field which interests us quite a bit. Now, I guess I've seen that many of the people in your institute, also people I know very well, we all have witnessed the rise of linear optical quantum computation, which is now 20 years ago. And from the theoretical background, it's great that we only need a nonlinear network, photons, and things are done. Unfortunately, the whole community had to learn that's not as easy at that, because the resources you need for that are tremendous. And this is really, from the experimental side, a real challenge. Now you can do different things. And one thing you can do, look at something which is less ambitious and nevertheless gives you interesting insights. And this is the research line which we do in my group about quantum walks. And more broadly, I think this we can say is quantum simulations. And last but not least, in 2011, the field or the idea of boson sampling came up, which again shows us that we don't have to scale the system so tremendously. And for those of you who are not familiar with it, it's actually quite fascinating. You have a linear network, which has implements a certain matrix, a Hahn-Random matrix, and you put single photon states on the input. And if you ask to calculate the output distribution, interestingly, this can't be done if network becomes larger. So this is a computational hard problem. And this is quite interesting and intriguing that it is. And a lot of people set out to do these experiments. Now, last year in 2020, I think there was a breakthrough for photonic quantum computation, which was really quite fascinating in John Wei Pan's group, where they could show quantum computation advantage using photons. So what they really did was to implement a variant of boson sampling, and they implemented Gaussian boson sampling. And that's for me quite fascinating because back then we thought about how can we scale up photonic systems. And of course, you can use the hardware approach where you kind of implement real single photon sources. But then if you're coming from the quantum optics community, you know that the sources which we have available are actually not the single photon sources, but so-called squeeze states, Gaussian squeeze states. And those you can produce very efficiently. And you have photon generation probabilities. And these Gaussian states actually have good scaling. And this is really also when you look into that and you can ask them, if I also put them in the same type of matrix, is it still computational hard? And we had really good arguments, and it seems that this is really true, that the photon counting statistics, which I have to record there at the end, is equivalently also computational hard. And I'm telling you that because in 2017, this was the idea where we proposed it. And if you look back, what really was implemented, this is indeed what they have implemented. And as far as I know, by now, it's still computational hard. And this shows you what you can do with photonics if you think a little bit also from a concept side, how you should implement things. With that, I would like to switch back and go to my own group, and I would like to present my group a little bit more into detail, because it's not only presenting my group, which I'm very grateful they're doing the work, but it also presents a little bit the philosophy of the integrated quantum optics group of my group in Paderborn. My group consists of several subgroups, and one subgroup is the technology, and the subgroup leader here there is Christoph Eigner. And what we do there is we really fabricate devices, and we develop technology like lithium niobate, LNOI, KTP, and nowadays we're also looking in Piplin, and now we're also in LNOI. And we have the whole fabrication which we need for that: periodic polling, waveguides, bonding, dielectric coatings, and electrodes. Then these devices or structures are taken to the optics lab, and we built from that devices, and the group leader there is Harald Hermann. And this is one of the devices I will present later on. What you have to do for that is really you design the optic circuits where you give the design to the technology, and then you do the quantum characterization. And this is how you really can then build up quantum technologies. And the last subgroup in my group is quantum networks, and the group leader there is Benjamin Brecht. The quantum networks is really where we come from the theoretical aspects, where we implement experimental setups, but the motivation, what we implement, comes from theory. And there we look at ultra-fast pulse light and quantum source engineering with ultra-fast pulse light, quantum walks, and here you see quantum metrology, source engineering, topologies, quantum pulse gate, time multiplexing. I will show you results there. This is a circle, and it's not just a circle drawn as a circle, but this is really also the philosophy we pursue. I think for quantum photonics, if you really want to implement these complex systems, it's good to have all these different people competences in one place, and we interact quite strongly with each other. Okay, then let's have a look how do you scale systems? Because this is really at the end, and how can you build up larger systems? And actually in my group, we're pursuing different strategies for that. And in this talk, I don't show you everything what we are doing, but I want to give you some ideas, some general ideas, what is the research alliance about. And then I want to give you some examples. So we look for integrated optics. We look for time multiplex quantum systems. And the last thing I want to present you is we look at temporal modes of pulsed light. And at the moment, you might not see why this is a scaling effort, but I hope at the end it's becoming clearer. So let me get started with integrated optics, and let me be started a little bit more specific. What we are focusing here is on nonlinear integrated quantum optics. Now, I was coming to Paderborn 10 years ago, and I was going there because this is a place where it's an established space for producing integrated devices. When I was coming there, I was young and I said, well, I have all these fancy quantum optics idea. And then people told me, well, you know, a lot of these things we know. And it's actually true. There's a strong integrated optics community. And I think it's good that this strong integrated optics community is. There's a long history. And I brought you here on review for 1969, where you really see that already at that time, people had very similar idea. It's a review from Miller about integrated optics. And what I want to show to you is how quickly I can make this review extremely modern. So instead of integrated optics, I put everywhere in between the integrated optics quantum. So it's something about integrated quantum optics. Sometimes I have to replace laser beam circuitry by quantum beam circuitry. Good, here too. And sometimes this laser I have to replace by photon source. Now, this is a little bit more tricky, and I don't go into detail there. This is a technological challenge. But anyhow, we can also do that. And then let me read to you the last sentence. If realized, this new art would facilitate isolating the quantum circuit assembly from thermal, mechanical, and acoustic ambient changes through small overall size. Economy should ultimately result. If you ask what quantum photonic is about, this is, I hope it sounds very modern for you. Why is that? Well, actually, what we do, we keep the general ideas and we adapt them to quantum optics. And this is a real challenge, and this is where we are at the moment. Keep the good things and put the quantum on top of it. Now, let me go a little bit more into detail what that is. So this is now again a review from 2012, so a little bit more modern, from Alan Asburg-Gussig and Philip Balter. And it's about a photonic quantum simulator. And it's about hybrid integrated networks. Now, what you can see here is that we have a linear part. I talked a lot about linear circuitry, so beam splitter. And we have a nonlinear part, and then we have the detection part. Now, why is integrated optics good? And I had it already in that review. You have many spatial modes available and controllable, and this is for an optic system nice. You get interferometric stability of a large optical system. You can have rather compact devices, so you go in the direction of miniaturization. You have easy operation, whatever means easy. High efficiency, well, losses are an issue, yeah? But this is also what is kind of the promise here. And then this is the good thing about all of them. Then let's have a closer look into that. And there's that linear thing. And I'm sure that you have heard about integrated quantum optics. And a lot of these papers are actually about integrating just the circuitry. But already that has a tremendous effect. And I think it's fair to say that it started in 2008 in Bristol with Jeremy O'Brien's group, where they showed the first experiments. There's some examples, not just almost randomly picked. So it's not complete at all, but this is one example from Paolo Madaloni's and Fabio Carino's group in Rome. And this is a boson sampling experiment. This is Ian Wormsley's group from Oxford. And this field really took off. So there's a lot of work in this direction. One thing which has started later, and I think is still under investigation, is that nonlinear part. So how do we implement and integrate these things and scale it up? And this is actually what we pursue in Paderborn. So a lot of our experiments relies on the Lithium niobate platform. There we can have, it's an old established technology with low loss waveguides, such that we can minimize the decoherence. We get the stability and scalability for integrated optics in general way. Since the Chi2 nonlinear system, we have very efficient photon pair generation, which is nice. And we can have, which is, in my opinion, equivalently important, maybe even more important, is fast photon routing. After all, lithium niobate is one of the standard techniques to implement electro-optic modulators. This is kind of the vision, the implementation of complex quantum circuitries on the Piplin platform. And you can see what kind of elements you can have. You can electro-optically control phase shifters, single photon conversion to different wavelengths transducers, polarization control, because we have a system which is in titanium indifused waveguides that we guide both polarizations, and even detectors can be integrated on that platform. So this is kind of the toolbox of integrated quantum circuitry. We have the routing. This is the passive part, which you can also have on lithium niobate. Generation and also storage has been shown, photon pair generation, up and down conversion. I already emphasized the active manipulation. of electro-optic manipulations. And one thing which I also want to mention here is interfacing. So efficient waveguide fiber coupling and also mirror coatings where you can also implement things. All these components have been developed for classical optical applications, but tailoring a redesign and optimization of quantum applications is required. And this is quite frequently, you have completely different requirements in terms of length and how you really design your systems. Now, I told you that I will only show you some examples from my labs. And these are examples of things which we implemented the last years. We had heralded single photon plug-and-play source, which are heralding efficiency, raw heralding for around 50%. A noon state photon source, where basically you look at the outcome of a directional coupler. The generation of polarization entanglement, I like to call it a queer type source. And I think here in this audience, I can do that easily. You immediately will understand what I mean. So it's degenerate photon pairs, which has the same characteristics in terms of wavelength, but they're polarization entangled. And we also could generate free photon states on a chip, where we have basically one PDC section and then a cascaded second PhD, a second section on that. The system I want to show you more in detail is our homomantle interference chip, because it's the most advanced chip which we have implemented by now. Homomantle interference, I'm sure that most of you know what it is, but let me repeat it very briefly. It's a phenomenon if two photons imping on a 50-50 beam splitter, and you look where are they coming out. Well, if photons were classical balls, you would have these 4 different possibilities. But because of destructive quantum interference, these 2 possibilities cancel out, such that both photons leave the interferometer always at the same port. Now, this phenomena is the basis of measurement-induced nonlinearities. It's a fundamental quantum optical property. It's at the heart of linear optical quantum computation, and indeed of all kinds of different quantum networking applications. Here is a scheme, what that experiment is about. So we have 2 single photons impinging on a 50-50 beam splitter. We introduce a variable delay, and we detect these the photons at the output with a coincidence counting, the famous homomantle interference experiment. The time delay is 0. We see this bunching behavior, so there's no coincidences recorded. As soon as we introduce a time delay, we introduce distinguishability, and we get less interference. Other coincidences go up. Now, how did we do that? And what did we do in the lab? What we wanted to do is the monolithic integration of a parametric down conversion source, a 2-photon interferometer with a time delay. And this time delay we wanted to have integrated. And this time delay we wanted to implement for electro-optic components. So let me show you how we did it. The first section you see here was a photon pair generation with PDC light. This section here is a polarization control, and we switch the polarizations. So the photons are generated in H and V polarizations, and we switch the polarizations. You will see in a minute why we do that. The next component we have is a polarizing beam splitter, which splits these 2 photons. And then here we have again a polarization control, but this time it's segmented. So what it does, it switches the polarization of this H photon to V photon, such that they have the same polarization afterwards. But it does more. Because here, if you switch the first segment, you see that then the time delay between both of them are correctly set, and we get the bunching behavior. Now, if we switch at a different segment, we switch over the polarization at different positions. And because this is a birefringent material, this implies in turn that they have a different optical path length, so to speak, and we introduce a variable delay. The nice thing about this is electro-optic controllable, so it's very fast. And here, I showed you already, this is a 50-50 beam splitter, and it also can be controlled by electro-optic control. The theory for that is depending on which segment you switch, you get a different time delay, and this is what you would expect for PC1 for this one to be switched. And if it's on, if you switched it to the beginning. If we wouldn't have this switch at the beginning, if you don't switch, then we always have a time delay, and then we don't see the interference at all. This was theory, and this is experiment, and already see from the experimental data, from the raw data, that it seemed to work very nicely. Now, if you plot these data differently and recalculate these segments in terms of delay, you see nicely that we could record that homomontal interference chip. This is actually a device, so you see it's really on one monolithic block. And the benchmarks we received over 93% visibility and time delays of 12 picoseconds. Now, the nice thing about this thing is that it's really fast, and you could mention that this is one building block of a quantum communication network where you want to synchronize different events. With that, let me switch gears and let me talk now about the second strategy to scale photonic systems, and this is time multiplex quantum systems. Time multiplex quantum system we use to implement quantum walks going towards the direction of quantum simulations using photonics. Let me briefly introduce what we're looking at. We're looking at quantum walks in contrast to random walks. What is a classical random walk? I'm sure you know. Look at this little guy. He's drunken. He doesn't know where to go. He wants to walk on a line. But since he doesn't know where to go, he throws a coin. And depending on the coin, head or tail, he takes a step to the left or right. So coin toss and step. Well, if you repeat that over and over, and we go for every step, we have these different pins, then we can ask at which position does the random walker end up with. And I'm sure this is a golden board that you have seen that. What you will end up with is, we know it from maths, is a binomial distribution. In physics terms, we can say we have diffusive propagation, characterized that the variance is proportional to the number of steps. Now, if you want to drive that or bring that into the quantum regime, what you do again a coin toss. Now, the coin in this case, in the quantum case, is a two-dimensional Hilbert space. And then, depending on the coin, we do again a step to the left or right. And now we allow for interferences at every position, at every pin, so to speak. And then we look again at the output distribution. And this is what you get. Since a coin is a quantum state, we have a superposition which is occurring there, and we get completely different distributions. We get a ballistic propagation here, and you see already with that few steps that it looks differently, and the variance of this distribution scales with n squared. Now, with that few steps, you don't see much, but if you repeat that over and over again, this is over 100 steps, the red one is a classical distribution, and the blue one is a quantum walk, and you see a clear distinction here. So I introduced here classical and quantum again. Let me be a little bit more precise what I mean by that. So what do I mean by classical and quantum in this context? I assume that I have a single photon. This is kind of the particle nature of the thing, and this would be the classical situation. Now, if I go to the quantum side, I'm looking for that single particle on its wave properties. So this is nothing else like the wave-particle dualism in a complicated interferometer. And this is what's meant here by going quantum. Why is that interesting to look at these quantum walks? Well, the motivation is that random walks is a mathematical model which is used in a lot of ways for quantum computation, for simulation of things. Like Brownian motion is a classical process which can be described by random walks. Biological system can be described like a deer wandering. And in information science, if you look what's behind the research engine, it's also a random walk algorithm. And this gives a motivation to look at quantum walks and go towards quantum systems there. Again, you can think about simulating semiconductor physics, quantum biology would be a field, and of course, quantum computation and simulation, the motivation I gave you at the beginning. Now, what is a good platform? Again, it's about scaling, and this is a private personal view, but I would like to come up with different benchmarks, so to speak. If I really want to have a good optic photonic systems, I need these things. I need reconfigurability, I need a high stability, I need scalability. And here, just from the very beginning, when people started to look in, how can you do that? Well, reconfigurability, bulk optics is good. Stability, integrated photonics is good. But to combine all of that is challenging. And one thing which we had been looking in for quite some time now is time multiplexing, because it's a platform where these conditions can be met quite nicely. So let me show you the physical apparatus which we used in a sketch, and then I explain you in detail what it is. So we have here a system where you have an input state, which we launch into a fiber loop, which is actually done by electro-optic modulator. Leave that out for the moment. We implement the coin by half wave plates and quarter wave plates. So polarization, degree of freedom is kind of the coin degree of freedom, and it's nice to be manipulated. And then we use a double loop structure, so to speak, a polarizing beam splitter, such that we split it into two arms, and these two arms have different arm lengths, and we recombine. The photons are then going back. Here, the partially of the light can be detected with photodiodes, and then we loop the system again. So let me explain to you how that works. So here's the input. The first thing the pulse sees is a half wave plate. And we have the coin operation, for example, the Hadamard operation. Now, this kind of double loop structure for the PBSs does nothing else but introduce a relative shift in time depending on the polarization. So this relative shift in time corresponds to steps in position space. So you see, depending on the polarization, we have either delay or not. Now we have taken one loop, we're coming back to the same again. So now these two pulses again see the coin and the same loop again. And what you see here, that two parts of this system, so which have been split again, meet again. And this meeting is basically now showing you the interference phenomena, and this completes the first step. And you can reiterate the system over and over again, and this implements your quantum walk. Now, I said, leave that EOM out here, this one. And this is really where the reconfigurability comes in. We can switch polarization optics by electro-optic modulators. And this electro-optic modulator is fast enough, and the loop is designed such that we can address every individual pulse, such that we really can also modify our circuitry. Now, this is actually quite old data, which I brought to you. It's a quantum walk over 28 steps, theory and experiment. So gray is theory, blue is the experiment. And this 28 steps is for the time multiplex quantum walk, would correspond to 406 beam split and 29 detectors. The probability distribution confirms a high degree of freedom. And the nice thing is, this time multiplexing in terms of experimental effort, it's rather resource efficient. And what you also can see that we have almost an ideal homogeneity. And this is really one of the advantages. This is simply because you're using the same elements over and over again. In a special implementation, you would have rather difficulties to do that. But here you get really very clean probability distributions from that. Now, as I told you, I'm just showing you some examples. I'm happy to talk about the circuitries later on if you're interested in that. But we have implemented all kinds of different time multiplex circuitries. Decoherence disorder, losses. We also showed that you can expand the scheme to two-dimensional, but it's a truly two-dimensional quantum walk. We looked at percolated graphs, graph engineering state transfer. Then we kept going and simulated semiconductor systems with topological invariance. We looked at quantum walks with four-dimensional coins such that we changed the graph structures, and even measurement-induced quantum dynamics can be simulated in this system. Note that up to now, I was always talking only about one single particle. At that point, I want to come back because, yes, you can do all these things, but I would like to come back to a fundamental question here. And this is what I have been asked a lot on these talks, and this is what makes a quantum system quantum. And I'm sure that many of you have realized that this was just a coherence phenomena. And in fact, I said I was using a single photon. This was only partially true. I was using a laser pulse, which is an average a single photon state, but it was a coherent state. So the question really is, what's happening in these systems if you're going to many particles? And the way I would see that is going from a picture where we treat these photons as single particles from classical to quantum with a wave particle dualism. To go to multi-particle effects crosses the other border, so to speak. So this is a little bit more complex. And this is a quantum optics view. Here, with the multi-particle effects, now we're talking about horizontal interferences. And this is really where we wanted to go to. And it took us quite some time because we did all kinds of other experiments. But here I present you one of our latest results, which is quantum walks now with photon pairs. So we had to design for a quantum walk with a quantum source which is compatible with this circuitry. And I'm happy to go into details there, but this was one of the challenges. It's a type 2 parametric down conversion in the PPKTP crystal. It's an engineered source for pure single mode photons. Single mode, you will see in the talk, I mean really single mode in all degrees of freedom. And the challenge here, it's a picosecond source, such that the dispersion doesn't play a role. But anyhow, we could implement that. And then we wanted to understand what really is that difference between quantum and classical and these different coherences and what it is. And for that, we wanted to kind of do an experiment where we can see nicely how these different coherences of first and second order, meaning the coherence of just the wave or superpositions and second order horizontal interference really interplay with each other. And for that, we designed the following experiment. We launched into a quantum walk in this state generation system 2 heralded single photon states. And here they're kind of shown as red and blue. Then we implemented here in the blue part for our quantum walk, a quantum walk, which is a very specific circuitry in such a way that we implemented 2 different states. So at the output here, we're creating for the blue and the red photons in both cases superposition states. So what I mean by that here, this state with the double structure means that this blue photon is either at location 1 or location 2. And the same is true, or mostly at that point, for the red photon at location 1 or location 2. And then we look for horizontal interferences. So we let them interfere, and then we can detect coincidence. Second case, we did exactly the same experiment, but we introduced for the red one here in that circuitry an additional phase in between these 2 pins, such that we have a 180-degree phase change. So we change the classical coherence properties, the superposition properties between those 2 systems, such that we now have a different state here. And what we investigated then was exactly horizontal interference properties in 2 different ways. Namely, on the one hand, we did local measurements. And local measurements means a time-resolved second-order correlation measurements. What that means simply is that here we ignored this part completely, and looked just if we trace out all the other degrees of freedom, how is that horizontal interference happening? And then also for that, so we have a time-resolved detection, and what you get back is a nice horizontal interference dip. And it's true for both cases, and we see that the quantum character is indeed present in these local interference measurements. But then we also looked at the global property. And there we reminded ourselves that actually, since this is a single photon, we don't care if the photon came out from that port or that port. And the same is true for red. So we just looked at coincidence counts where, well, is there a coincidence either in one of these detectors which are blue or either in one of the detectors which is red. And this simulates a time bucket detection. And also the same for the other thing. So this is a global interference property. And here you see a quite distinct difference. While for the first case, these are identical superposition states for the red and the blue photons, you see again the nice home dip in this bucket detection scheme. You see something completely different for the system where you introduced that phase chip. In fact, you see nothing. So the quantum interference has completely been washed out. What that means is nothing else, but we can control with the classical coherence properties, so the G1 function, the second order correlation functions. And I think this is nice because it sheds light what these quantum circuitries really does. And that actually, in my opinion, the photons are the more fundamental entities of these systems. Good. I don't hear any questions. So with that, I'd like to continue and go on to the last part of my talk.
Christine, can I? Hi, Christine, Paul.
Hi.
Can I ask a quick question? So, what limits the visibility in your Hungo-Mandel dips?
Yeah, you observed it very well. Actually, in this Hungo-Mandel dips, it was simply counting statistics at the end. We had the trade-off because it's a Rayleigh single photon state, so it's a 4-photon experiment with picosecond pulses. And we had a trade-off of running it at low enough rates such that we still could get clicks and avoiding higher photon number contributions.
I see. Okay.
And we've got one more question. Ujan, you want to go ahead?
Yeah, thank you. So my question is, once you introduce the phase shift, do you immediately go from a quantum behavior to a classical behavior, so to speak? Or is there some sort of a transition in between the two? Like, can you tune the phase shift in order to get some sort of a,
You can. You will understand,
so to speak.
You will understand in a minute. I'm actually preparing for the last part of my talk. This was really a 180-degree phase shift.
I see.
And I can spoil it already. If you integrate over these two states, you see that they're completely orthogonal. If you understand them as global states, and thus you don't see any quantum interference. In fact, we also did this with free bins. If you look at that publication, and you can really change these visibilities according to the overlaps.
I see. Okay. Thank you.
Okay. Good. Great. So let's continue to the last block of these things. So we have seen integrated optics, and now we have seen about time multiplex quantum walk. Now let's go about temporal modes of pulsed light. And this is at the beginning, you won't see why this is really also a scaling application, but it actually also is. So let me get started there. What do I mean by temporal modes? Well, temporal mode encoding or temporal modes in general is an encoding which is a time frequency encoding. Now, if you're talking about time frequency encodings, what we just saw were time bins. And there you look at different times. Different times corresponds to the alpha pattern. You can look at superposition of different things. There's a perfectly fine encoding. But what you do is you completely ignore frequency. You can do the opposite. You can say, I'm not caring about the time at all. I'm just do a frequency encoding. So there's very defined frequencies and I don't care about the timing at all. If I'm talking about these pulse temporal modes, which I will do, this is something in between. So this is again, the time frequency phase space. It's actually really a phase space. You can model them as chronocyclic Wigner functions, but this is just the right side remark. And then all of these modes I will be talking to have in time and frequency, well, these structures. And you see, well, they overlap or they're on top of each other. But they kind of really have a very strange structure. And you might ask, why is that interesting? Why should I look into that very weird encodings? One motivation for that is that this is very much in analogy to spatial modes, and there you much more use the Laguerre modes, and this is the same thing in time frequency space. The advantage of this system is that you can define a high dimensional alphabet with them, and because it's time frequency, they live typically in our systems completely in one single spatial mode, but means nothing else that they're completely compatible with waveguide devices and fiber networks, and in principle they're even tolerant to any dispersion. So they don't care that if there's mode dispersion in that. The difficulty in these systems is how do we measure them and how do we manipulate them. Now, this is just an introduction. Let me go a little bit more into detail on what I mean by that. If you hear about quantum optics in your standard lectures, what you typically do is that you start with some quantization volumes whatsoever, and you talk about the modes, but very quickly you arrive at the system where you say, and then we have a monochromatic mode operator, and now we can quantize the system. And you do for these monochromatic modes the field quantization, and you don't care about these mode structures anymore. Now, if you think about that, this is definitely not the whole story, because if it was a monochromatic mode, you Fourier transform that, and this is a system for the photon which has an infinite time, a bit rate of 0. So no physical system can be really a monochromatic mode, and particularly not if you're talking about quantum communication systems. So I do have to do something differently if I really want to go for practical systems. And this something typically is really that you define a mode operator in some sense. What is it? I'm doing, well, I kind of get a wave packet defined as a coherent superposition of different frequencies where this single photon is living in. This is the temporal mode operator. If you Fourier transform this system, you know very well that the Fourier transform of Gaussian is again a Gaussian state. And we have also a confined system in time. And what we have done, we have now introduced that envelope function f of omega. If you accept this system, however, that they are envelope functions, you can now play with these envelope functions. And this envelope function could, for example, be the Hermite modes. But we also know that Hermite modes are basis functions in that integral form. And this actually is the idea of a temporal mode. So every envelope function defines you a different envelope, a different temporal mode. In terms of theoretical modeling and systems, these temporal modes are completely equivalent to monochromatic modes. So they are orthogonal modes, and you can encode on these informations. So in that sense, they are very similar. So they are really independent from each other. The only problem is that they overlap in frequency and time. And if I say overlap, I don't mean this overlap in really mathematical terms, because they are orthogonal, but they're living in the same time and frequency domain, if you want to, so to speak. And you can't just measure them by measuring either time or frequency separately. So how do we actually deal with that? How comes this idea, or what did it come from? And it actually comes from parametric down conversion sources, which were pumped by a pulse pump. And here, this is nowadays a rather prominent topic, and I'm sure that you have heard about that if you have very specific dispersion properties and you pump a waveguide by pulsed light, then in general you get a rather complicated system here with different temporal modes present. We call them Schmidt modes. And then you engineer your system such that here, this is a typical plot of this source engineering. This reflects basically the property of energy conservation, which is the one part. The second part is momentum conservation, but this basically tells you that dispersion properties also have some specific shape. And if you combine them, or if you engineer the system nicely, you can have a system where this so-called joint spectral amplitude function is a circle, meaning is a product of two functions decorrelates. And this is exactly the scenario which is also shown here in the picture. And thus you can generate out of one Gaussian pump pulse really nice pure single photon wave packets. This is exactly what we used in the quantum walk experiments. And I could talk more about that. I'm happy to go that. But in this talk, I would like to go in a different direction. You can now start in shaping the pump pulses differently. And this will change here, this first function of the pump pulse, which is defined by the pump pulse. And you get fancy looking joint spectral intensity functions. And then you can interpret them in your Schmidt basis in a different way. Basically what you do, and this is what I want to say, that you engineer the generation of your photon pairs. And if you're in that scenario where we were at this nice source engineering system, if I take the third Hermite functions, I excite exactly 3 modes, and I'm creating a state which is entangled in these 3 modes. And this is the nice thing. I will show you in a minute more in detail. I told you the difficulty if I want to use these modes is I have to kind of be able to address them. And for this, we developed the concept of a quantum pulse gate. What is that quantum pulse gate? Physically, it's a sum frequency generation process, which we also engineer, and I will tell you more in detail. But from the encoding point of view, it operates in the following way. We have an input signal, which is encoded in these temporal modes. For example, this parametric down conversion state, just the upper part here. And we want to have a system which only addresses one of these temporal modes. Here, in this case, first of all, just the Gaussian beam. We need a knob, and for some frequency generation, this is really the pump pulse for the some frequency generation, which is shaped appropriately also in that first Gaussian mode. And you see here at the output, all the other modes are unaffected, and just the one mode which we are addressing is converted to different frequency. Now, if we switch to a different pump shape, then we leave the other modes unchanged, and now we only convert the first Hermite function, and so on. For that, we need a specifically designed some frequency transfer function. So this is the input frequencies which are allowed, and this is the output frequency, and it has to be a very, well, a system, an ellipse basically, which is aligned along the main axis. Now here, I go a little bit more into detail about these parametric down conversion in waveguides. Just repeat something from the experts. I told you that we have, if we just pump it normally, we have a joint spectral amplitude function where we have these correlations occurring. We do the Schmidt mode decomposition, and here you see that in general you get a system with a rather complex mode structure. Now we can go to that other system which I just told you, where we have the decorrelated states, and this is the pump mode basically, and this is experimental data. It looks tilted, but it's actually not so much. It has a slight tilt, and this is what I explained to you is the source engineering. What you can do is that you now do these different pump modes, and then you see that we really get all these different joint spectral amplitudes according to the pump function. And here for all of them, you see that in this case, we're exciting exactly 2 modes. Actually, this is a Bell state and temporal mode basis. Here we have 3 modes, and you can make them such that the Schmidt mode decomposition is actually equal for all of these things. So basically, that means we can control these modes very well. The quantum pulse gate, I also explained already to you. Here we have, again, illustrated what I just showed you. We have that input beam. We have the pump here in that function, we convert it, and there, depending how we want to convert it, we address different modes. Now, this is the theory of the quantum pulse gate. The realization, if you look into detail, is a group velocity matched some frequency generation. For this some frequency generation, we have energy conservation, that the converted light equals the pump light plus the input light. This is the K vectors. And the interesting thing is because of the group velocity matching, that the efficiency of the quantum pulse gate is dependent on the power. Okay, that's fine, but we can adapt that. And then it depends only on the overlap between our pump and the input frequency. And this is basically the trick. And this is also why we need that very specific form of a transfer function. Again, I'm happy. This is more for the expert to go into details if you want that. From a technological point of view, for implementing the system, we use a home-built periodic pole lithium niobate waveguide, 4.5 polling period, operated in 190 degrees. It's a type 2 some frequency generation process. For that, we need the titanium diffused waveguides, and it's operating at rather convenient wavelengths for us because this input signal has to be a signal which is around 1550. So this is highly practical. So it's a telecom wavelength. The pump photon, which we have to shape, is around 860, also quite nice, because it's exactly types of wavelengths where a lot of pulse shapers are actually, well, available, or we can easily build them up. Now we implemented this system, and the first thing we wanted to show is that we can select arbitrary temporal modes, and if we can do that, we can also select arbitrary time frequency time band superposition states. This is a side remark. But this is a result from 2017, where we reconstructed the PVM elements of a 7-dimensional basis, and we could implement all mutually unbiased basis states. And by now, we can also go to higher dimensional PVMs. And this basically shows you, yes, we can now do an information encoding. We have the measurement in place so that you can really study different encodings on this high-dimensional Hilbert space. What I want to show you here is that we did the next step, that we basically did now temporal mode tomography. of a designed multi-mode PDC system. Now, this is the system which I showed you before, where we designed the whole system such that we have only one output system. And then we did pulse shaping, and we have this joint spectral intensity. And this is the tomography. Here you see which of these temporal modes, HG mode, should be occupied, theory and experiment. And we were quite happy because you do the shaping such that you expect that only 2 of them are occupied. So this is what you expect. And you see from a tomography that you clearly can see that. You see that some of the off diagonals are also occupied. It's not perfect, the tomography, but it works pretty nicely. We use for that this 7-dimensional tomographically complete set. And of course, we also did that. Here you see when we do the pump type such that we go in the normal system of source engineering, where we expect that only one of the elements is occupied. And you see that this also worked quite nicely. And then we did it for correlated state, and you see also the equivalence here. We characterized the purity also from G2 measurements, by just the marginals. This kind of can give you that, and there you also see the numbers coincide quite nicely. One warning, and this is why I bring that up again, I see quite a lot of people say, oh yes, I have these joint spectral intensity measurements, thus my state is decorrelated. Well, not really. What we did deliberately is we introduced a phase chirp. So you don't see that in intensity measurements, but if you do that tomography, we could nicely see that we are driving the system towards multimode. And here you see the data for that. Well, the reason is that you're simply introducing time correlations, which you don't see in that intensity correlation measurements. But this is also more like a side remote mark here. Last topic, I try to be brief. Once we have implemented now this tomography or quantum pulse gate, where we can now operate in the time frequency domain on arbitrary superpositions, we realized that's also very useful for other applications. And here I'm talking about systems for parameter estimation for incoherent emitters. So let me say what it is about, and it's easiest to say in space. So it comes from idea that you want to observe the distance of 2 stars from astronomy. And this is incoherent light, which impinges on your detector. And you make this distance smaller and smaller. And you ask yourself, how long can I still estimate this distance? What you can do in space, you can also do in frequency or in time. Now, this is a simulation for different distances. Here you see clearly that you can resolve the distance, but it's getting smaller and smaller. Then you see at some point the variance, it's very hard to distinguish these 2 distributions. Now, the mathematical formulation is that you have the separation on that axis, and you ask for the Kramer-Rao band. So what is the variance of its estimated parameters? And this is the intensity counting, but you look into that. You can't resolve them. And this is, you know that very well. You learned it in the basic lectures. This is the Rayleigh curves, the Rayleigh resolution limit. If they're getting too close, you can't resolve them anymore. The interesting thing is, in 2016, Zhang et al., Zhang, Nair, and Lu came up and said, well, but this is not the quantum limit. So if you calculate the quantum Kramer-Rao band, you see that there, this Rayleigh curve is actually not present. But with mode selective measurements, you can do better. That means nothing else. If you have mode selective measurement available, you can beat Rayleigh's curves. Now, interestingly, our quantum pulse kit is doing exactly that now in the temporal domain. And this is what we implement here. We programmed different separations, and we estimated these separations with mode selective measurements. And here you see the Kramer-Rao band, and you see nicely this is a classical limit, and this is a quantum limit, that this works nicely for our systems because the quantum pulse kit is actually operating on these coherent superposition states. You can get one step further. So up to now, I was just having 2 emitters with equal height, and we just wanted to estimate this distance S. Actually, in a practical system, it will look differently because these 2 systems can have the 2 emitters can have different intensities, and also the centroid it can have a different centroid. So the question is for this multiparameter estimate, that they have a multiparameter estimation. So the question here, which you have to solve, that we have two incoherent point sources with unequal intensity, some separation S, and a centroid S0. And the question is, how well can you estimate these three parameters simultaneously, which you want to do in practice? And what measurements do we have to implement? Here you see the work from our collaborators. And for the experts of you, that's quite interesting because these parameters we have correspond to quantum variables which do not commute. So it's also from a fundamental point of view quite interesting, this multiparameter estimation. Now with our quantum pulse gate, we could implement these systems quite nicely. Here you see a whole bunch of different measurements where we see that, we implemented two different signals which unequal heights, and we estimated exactly what I showed you about the distance between them, the centroid, and the different heights. And then you do with the pulse gate these mode selective measurements, and for all of them you can see that you're very close to the quantum Kramer-Rao band. And I think that we demonstrate that we have a nice tool now available where we can do kind of nicely these kind of super resolution measurements which are done by mode selective measurements. Okay, the quantum pulse gate measurements with adaptive gate impulses give us these results. With that, I would like to sum up. I showed you our work on linear integrated optics. I showed you our work on time multiplex quantum walks, at least some examples. And last but not least, I talked about temporal modes to you. And with that, I would like to thank you for your attention. But I also would like to highlight that this is, of course, not my work alone, but it's actually the work of a lot of people who are behind the scenes. And I'm really quite happy about the group who is really doing a great job there. So thank you very much for your attention.
Thanks for an excellent talk. That was really interesting. Does anybody have questions? Before I, no?
Yeah,
So,
I have one
oh, Paul.
for me.
Oh, Ujan, okay.
Yeah, in the beginning of your talk, you spoke about the interconnects between the electro-optic modulators and the fiber networks.
Interfaces.
The interface, okay.
Yes.
Could you talk a little bit more about that?
Yes, so if you have a lithium niobate chip, you kind of have to have very efficient coupling between this lithium niobate chip, the mode, and the optical fiber. Now, there are different things which attribute to that. The first thing is how equivalent are the modes per se. And there I hear sometimes that this is a big issue. Well, it depends what you call big. So this is, theoretical overlap is 93%. You can say it's big or short, but anyhow, it's not the major problem in principle. There's an alignment issue there. And there we're also working that, but this is the limit. And then there's the refractive index change, so you need AR coatings. If you do everything properly, you really can go very close to that. Well, I think we said 85, 89%. And if you're interested in that, we had this plug and play heralded single photon source where I told you that we have 50% raw close coefficients, coincidence versus singles. Now, where are these 40%? I have to tell you that was pump suppression. So we had to introduce fiber break gratings, which was really not the problem of the interconnect. So this is the technicalities. If you want to go beyond that, you have to work harder. And we're also looking into that because we're aware that for quantum technology, this is an issue. This is kind of the nasty engineering work behind the scenes.
All right, thank you.
Christine, you of course had all your integrated optics stuff, and then you had your time band multiplexing stuff, all of which is independently beautiful. The question is if you can combine them. Of course, the issue is if you're doing the time band multiplexing on a chip, it's hard because it's hard to get enough of a time delay in order to do many loops. But I guess I'm just wondering what your perspectives are for that, you know, going forward. As we know, bulk optics are nice because they're pretty low loss, but then you have to stabilize these big interferometers and things like that. What's your current perspective?
Okay, it's very related to the question which we just had, right? The question is how well can we get these interconnects? And I personally think these two approaches we can combine them. In fact, we do have an experiment at the moment where we have a source inside such a loop. Okay, it's not published yet, but it's doable. It's kind of hard from a technological perspective. You have to engineer and you have to work hard to get these couplings into these systems. But honestly, there's no reason that you can't put things together. And we're getting better. And think you just demonstrated with the time loops how efficient you can get.
Mhm.
And at the end, it's a question of doing. And I think this is why we're pursuing both approaches. And if you look what we hear from also people who want to scale up system, they kind of also think along the same lines. And if you really, really, really want to scale up, you probably have to do these things. I think we will, at some point, we will see that it's doable. Our technologies really also, we photons people, I still say we are spoiled because we could use all this technology which was there or from telecom, and we didn't develop our own technology. Now we have to develop, and now we are, oh, it's so hard. Yes, it is hard. But I think I really want to advertise that a little bit. We have to do more technology, and then we will be able to do fascinating physics. And I know that you guys do that. It's a question of engineering, but it's not a physics question anymore.
Right.
But we can do beautiful physics with it then afterwards. That's the thing.
Yeah.
Bryce, do you have a question too?
Oh yeah. So just a question about the final part. Thinking about using these time frequency states for qubits or things like this, what's sort of the level of the detection fidelity for single photons currently with this SFG based readout? The one that gives you the mode selectivity by SFG?
Yeah, I fully understand. So the fidelity, the post-selective fidelity is excellent. So there, I think we have, you see that in these pulse gate measurements. Let me try to go back. I think we have over 90% fidelity for implement the POVMs, okay? So this is really operating nicely. That's not an issue. So if you look in this, no, sorry, it's one back. In this paper, you see it a little bit from the graphs already, but if you look the POVM elements, how well can we implement these projections? Yeah, the fidelity is, I think, 97%. So this is not the issue. There's a second issue if asking me about single photons. This is efficiency. And considering the efficiency, we have the couplings issues, which we just discussed. And then we have, again, what is the efficiency of some frequency generation processes. And in particular for the pulse systems. Now, you know that in general, and again, I'm talking to experts here, the efficiency of some frequency generation can be really high. Now, for these pulse systems, we have an additional problem because time ordering effects kick in. And you probably know Mike Raymer from Oregon, but he showed how you implement also these things with high efficiency. There's no limit in general. So this is kind of, so without, if you're not caring about efficiency, you have a very high fidelity already. For efficiency, again, you have to fight for. But in my opinion, it's again not a physics question.
And maybe just as a follow-up, I guess so I think it's not a limitation maybe, but if one tries to envision sort of like a passive mode sorter similar to what you have for OAMs, I guess would that involve something like an interferometer with some highly dispersive medium in one arm or something to sort of flip the phase frequency?
Yeah, but as far as I know, if you just use this, I would say if you only use passive and not, I'm pretty sure about that. If you don't use some frequency generation, you can't select on superposition modes. And this is the problem. You can only then go again back to projections on in frequency or time, and then it doesn't work. So this is why this quantum pulse gate is necessary, because you have to do projections on frequency superpositions, and this is the hard part. And it's not possible with passive elements only because you always need a gating in between. We know that from ultra-fast optics community. So if you ask about frog and spider and all that, there's always some active element in there.
Okay, thanks.
All right. Well, it seems there